All right, let's work through this together now. G is a group with order 15. We're supposing that G has exactly one subgroup of order 3 and exactly one subgroup of order 5, and we're trying to prove that G is cyclic. The initial thought you hopefully have is that means we need to figure out the generator for G. The question then is how to get there. It's got exactly one subgroup of each of these orders, 3 and 5. 15 is 3 times 5. Both 3 and 5 are prime. The fact that they're prime is going to be relevant. So we could start by saying let H be the unique subgroup of G with order 3 and K be the unique subgroup of G with order 5. You don't have to necessarily start the proof that way, but it seems fairly logical to me to start that way. 3 and 5 are prime. What can we say about H and K? Based on the fact that 3 and 5 are prime. They are cyclic, right? That's a consequence of Lagrange's theorem. It was one of the corollaries. Since 3 and 5 are prime, corollary of Lagrange's theorem, or you could just say Lagrange's theorem. Lagrange's theorem implies that H and K are cyclic. Say, you could say something like H is generated by A and K is generated by B, where the order of A is 3 and the order of B is 5. And then if you wanted to be even more specific, it's probably not absolutely necessary, but you could list out the elements of H and K. So H equals EA squared. H is order 3, so that would be the end of H. And K equals EB, B squared, B cubed, and B to the 4th. You could do that. It's probably not necessary to do that, but just if it helps it make it feel more concrete for you. And these are, again, the unique subgroups of orders 3 and 5. There are no others. Therefore, what can you say about these elements? They are the unique elements of what? A and A squared would be the unique elements of what? If these are the only, if that's the only subgroup of order 3. Nobody wants to say? And the unique elements of order 3. Any other element of order 3 not in that list would generate another cyclic subgroup of order 3, and there isn't one by assumption. And likewise, these would be the unique elements of order 5. Altogether, the size of the set H union K, which by the way, H union K would not necessarily be a subgroup. In fact, it would not be a subgroup of G. Intersection of any two subgroups is a subgroup, but the union in general is not. But I can still use order notation to say how many elements. And the only thing they have in common is just E, right? Because these things have order 3, these things have order 5. They can't be the same elements. So the number of elements total here would be 7. But the order of G is 15. There's 8 more elements that haven't been accounted for. Let C be one of those 8 elements, be an element of G that's not in the union of H and K. Maybe I should say therefore G set minus H union K is non-empty. What's a set minus? Everything in G that's not in H union K. There's 8 elements in it, so it's non-empty. Take one of those elements. We might hope it's a generator of G. What guarantees that it is? It will be. What would guarantee that C is a generator of G? It would have to be order 15 because of what theorem? Lagrange's theorem. Lagrange's theorem implies the order of C, which is the order of the cyclic subgroup generated by C, is either 1, 3, 5, or 15, one of the divisors of 15, but it can't be 1 because it's not E. It can't be 3, it can't be 5 because we've already listed out the elements order 3 and 5 and they are in H union K. It's got to be 15. But by what we've already done, by what has already been said, the order of C is not 1 or 3 or 5. Therefore, the order of C is 15. Therefore, G is generated by C, and therefore G is cyclic. By the way, each of these last 3 things counts as a sentence. The 3 dots means therefore. That's a sentence, that's a sentence, that's a sentence. Those are complete sentences just with symbols. So that's fine. Okay, maybe a little bit more wordy than I needed to be. Showing a little bit more detail than probably I needed. In fact, if you look at, this is a practice problem. If you look at the answer key, I believe in my answer key, I did a shorter proof. On a test, it's hard in the time pressure of a test to write short, clean proofs. But then on the flip side, if you make your proofs too long, then it takes too long. I mean, it's a struggle, balance. I would encourage you to try to write a shorter proof of this as well. Maybe you did. And yeah, I could see putting something like this on the test. Maybe a different example. Maybe the order of G is 21, which is 3 times 7. Or 35, which is 5 times 7, or something like that. For the graded problem due on Friday, again, that you will be emailing to me, since we won't have class on Friday, you'll be doing a similar problem, number 54. I wrote use 27 there. Well, it's really use the method of 27. Maybe the fact in 27 is useful as well, but G is a group of order 105 with the property that it's got exactly 1 subgroup for each divisor of 105. Prove that G is cyclic. Okay, it's probably a similar strategy will work. You don't have to list. Again, you don't have to do this listing. That was extra. I didn't really need to do that. But it might have felt it, make it more concrete in your mind. All right. What I'd like to do now is I'd like to move on to chapter 8, which you have not even really read about yet, according if you followed my plan. Get you going. The practice problems that you should work on before Friday, recommended, are from chapter 8. The graded problem is that one problem from chapter 7. So I'd like to do that for, I don't know, maybe about a half hour here. And then at the last 15 minutes or so, I'd like to go back to chapter 7, actually, and encourage you to really put some good effort into your reading. Maybe you have, maybe you haven't. Whether you have or haven't, I would like to spend 15 minutes really just trying to give you some insight into this pieces into the reading and encourage you to really take it seriously, but also maybe even enjoy it. Chapter 7 is what the kind of stuff that group theorists love, okay? Lagrange's theorem and all its applications, the Orbit-Stabilizer Theorem, all pretty cool stuff in the minds of group theorists, okay? So I would like you to even say, hey, this actually is kind of cool, fun stuff, and I want to take the time to really read it and understand it. All right, but let's start chapter 8, and I'm going to start chapter 8 not in the same way that the book does. I'd like to motivate the content of chapter 8 by talking about linear algebra a little bit, vector spaces. In linear algebra, one prominent example of a vector space that you consider is R2. Now, when you see this symbol, there's a bunch of different ways of thinking about it. You can think of this as being the plane. If you want to think of a geometrically two-dimensional plane where every point has real coordinates. You could think of it as a set of points, set of ordered pairs, where the coordinates of the ordered pairs, or components, sometimes they're called coordinates, sometimes components. Usually you call them coordinates when you're thinking about plotting, and call them components when you're thinking about these as being vectors. We can be free to call it either thing we want. X and Y are elements of R. As a set, you don't have to visualize that, right? You can just think about it as a set of ordered pairs. When we visualize it as a plane, there's actually not a unique way to do that either. There's the standard way called the Cartesian coordinate system, rectangular coordinates, where you do imagine graph paper, essentially, your x-axis, your y-axis, and then a bunch of vertical lines at, say, integer values of x, a bunch of horizontal lines at integer values of y. That is the standard way to visualize such a set, but it's not the only way. One thing that you do in linear algebra is change of basis, which effectively takes your standard basis vectors and makes them new, and maybe makes the coordinate system slanted in some way, skewed. And you might wonder, why would you ever do that? Well, if you took linear algebra, that actually should have been talked about. Change of basis is useful for diagonalization of matrices, and that's useful for solving problems like with differential equations or difference equations or something like things like that. But anyway, I don't want to get into the details of that. I just want to say this is a standard thing to think about in linear algebra. How's it related to group theory? Well, vector spaces are groups under addition of vectors. By the way, I also don't have to think of these as points or row vectors. I could think of these as column vectors. Maybe I should say, or R2 is the set of column vectors. Usually when you write them as column vectors, then you're more prone to say I can add them. Whereas when you're thinking of them as being points or row vectors, you technically still can add them, but it's maybe feels less natural. Either way, to think about it is okay. It's nice to think of them as column vectors, because then when we think about applying linear transformations from R2 to itself, for example, we can use a 2x2 matrix, and we can take your 2x2 matrix and multiply times the column vector to find the outputs. That's why it's nice to think of them as column vectors. But I probably will mostly write them as row vectors, actually, or points, because that is the perspective that the textbook here takes in chapter 8, thinking of this thing as a bunch of points. And it's also related to something else. You could also write that R2 is R cross R, where that cross, well, it looks like a multiplication symbol. Is it a multiplication symbol? Not in the usual sense. I think I talked about this earlier in the semester here. Does anybody remember when you take two sets and you cross them? What's that called? Or maybe you remember from another class. It's in honor of Descartes still. Yeah, Cartesian what? That's right, Cartesian product. I should capitalize the C in honor of Descartes. Cartesian product is what that's called. And you can form the Cartesian product of any two sets. Doesn't have to be R with itself. It could be finite sets, A and B. It's just a new set that's the set of all ordered pairs. Hey, that's exactly what this is. Set of all ordered pairs. If the set itself is finite, if I'm taking the Cartesian product of A and B, where A and B are finite sets, then A cross B will also be a finite set. And the number of elements in A cross B will be the number of elements in A times the number of elements in B. Does that make sense? If A and B are finite sets, I'm not talking groups here, I'm just talking sets, then A cross B, the number of elements, its cardinality, its order, if you want to use the word order, is the cardinality of A, the number of elements in A, times the cardinality of B. Nothing about group theory there, though it does apply to groups. If A and B were groups, and we decided for some reason to form their Cartesian product, then the number of elements in the Cartesian product would be the number of elements in the first group times the number of elements in the second group. You might wonder, can the Cartesian product be a group? Well, this is a group under addition. We're not thinking vector spaces here because we're sort of ignoring the scalar multiplication. We can, of course, multiply vectors by scalars, by numbers, but we're sort of just ignoring that when we think about vector spaces as groups under addition. They are groups. In fact, they're abelian groups. Infinite abelian groups, right? There's infinitely many choices for X and Y here. But this is a group under addition. Component-wise addition is what you say, or coordinate-wise addition. A comma B plus C comma D is defined to be A plus C comma B plus D, just like you did in linear algebra. Add these two vectors by adding component-wise or coordinate-wise. It makes it a group. An abelian group. What's the identity element? Of this group, additive group. 0, 0. And the additive, it's an additive group, so the additive inverse of A comma B would be the vector, the element whose coordinates or components are negative A and negative B. And it is associative, and it is certainly closed. It's a binary operation. And yeah, 0, 0 is the identity. The zero vector, if you like. We often visualize vectors as arrows as well, and that's useful for physics, but I'm not talking about any arrows here. So evidently, with R cross R at least, the Cartesian product can be made in a group under a component-wise operation. That generalizes to arbitrary groups. Given two groups, say G1 and G2, G1 cross G2, that Cartesian product is a group when the operation is defined component-wise. Or coordinate-wise. You can use either phrase, component-wise or coordinate-wise. In other words, to multiply, so we'll use multiplicative notation here because that's what we do typically in abstract group theory. The ordered pair G1 comma G2 with the ordered pair G1 bar comma G2 bar. You get the ordered pair whose first component is G1, G1 bar, and whose second component is G2, G2 bar. And it's implicit here that this is a multiplication in G1. And if the operation of G1 was more like an addition, we'd actually use a plus sign instead, just like we do with R2. And this is a multiplication in G2. And again, if the operation was an addition, it was more natural to use a plus sign, then we would use a plus sign. But again, in the abstract group theory, we always, just for sake of simplicity, and it's a time-saving device, just write multiplicative notation. This is actually not the notation that our book uses for this group. It's called an external direct product is its name. External direct product. And I don't know, I kind of think it's unfortunate. Our book writes this as G1 with a plus sign and a circle around it, G2. This is actually not completely standard across every group theorist. Some group theorists go ahead and write the cross there. Why write some different notation? I don't want to get into the details, but some, including our author Gallian, finds that a better thing to do for some other reasons that I'm not going to get into. But it really does as a set, it really does represent the Cartesian product. It is still the set of all ordered pairs. And in the abstract, we still write a multiplication for those operations, even though the notation uses a plus sign. Okay. Let's start with a simple example. How about, well, really simple. How about Z2 external direct product with Z1? Or if you prefer, the external direct product of Z2 with a trivial group with one element, call it 0. I'm calling it 0 since the operation in Z1 would be addition. I could call it E if I preferred, if I thought of the operation as multiplication. As a set, what is this? It's the set of all ordered pairs, where the first component is from Z2, it's a 0 or a 1, and the second component is from Z1, it's just a 0. In other words, the second component has to be just 0. There's only two elements here. 0, 0, and 1, 0. It's a two-element group. Yeah, the number of elements is 2 times 1, 2. A little bit of thought reveals it's going to be isomorphic to Z2 itself. Make a quick Cayley table. 0, 0, 1, 0 up here, and then over here on the side, 0, 0, and 1, 0. Think of the operation as being addition. 0, 0 is the identity. It is the 0 vector, if you want to go ahead and call it that. And 1, 0 is its own inverse. 1, 0 plus 1, 0, the operation would be plus. Is 1 plus 1, comma 0 plus 0. We're modding by 2 though, in the first component at least. That's 0, 0. All right, let's up the level of complication a little bit and consider the external direct product of Z2 with itself. Now it's got to be a 4-element set, right? 2 times 2. 0, 0, 1, 0, 0, 1, and 1, 1. It's fairly easy to prove the external direct product is a group. I mean, that does take proof, but it's pretty easy. It's because the components are groups. The elements in the components are from the individual groups. The identity element would be E1 comma E2, where E1 is the identity in G1 and E2 is the identity in G2. The inverse of an arbitrary element would be an ordered pair whose first component is the inverse of G1 and whose second component is the inverse of G2. It's pretty easy to prove these things. So this is a group, 4 elements. Is it isomorphic to Z4? Is it cyclic? Got a guess? A quick guess? I won't bother making the Cayley table. Instead, I'll compute orders. Both components are done mod 2. We get 0, 0. The order of 1, 0 is 2. Likewise, the order of 0, 1 is also 2. And the order of 1, 1 is also 2. Therefore, is it cyclic or not? No. So this is not isomorphic to Z4. It's a non-cyclic group of order 4. One classification fact that can be proved is that up to isomorphism, any group of order 4 is either isomorphic to Z4 because it's cyclic, or it's isomorphic to this non-cyclic group of order 4. There are only 2 groups up to isomorphism of order 4. I think I've already mentioned that at some point. Though I didn't mention the other one was this one. It's isomorphic to this one because we've never talked about external direct products yet. Okay, let's up the level of complication yet one more time. And consider the external direct product of Z2 with Z3. Zero, 0, 0, 1, 0, 2, and then 1, 0, 1, 1, and 1, 2. We might wonder, is this cyclic or not? Well, certainly, if you think about it here, the order of 0, 1 would be 3, right? Add that to itself 3 times, you'll get back to 0, 0. Or I should say, it's got 3 terms in the sum. There's 2 addition signs. Or think of it as 3 times 0, 1 if you're thinking of it as a multiple of itself. Or the multiple means added to itself. That one, think about that. That's also got order 3. This one, you think about it, it's going to have order 2. What's less clear is what the order of these two is going to be. Think about 1, 1. 1, 1 plus 1, 1. First component is mod 2. Second component is mod 3. It's a different operation in the components. Gets you to 0, 2. Adding this one to itself once gets you to an element of order 3. This element's got to have order 6. This group is going to be cyclic. Three, 1, 1 means 1, 1 plus 1, 1 plus 1, 1. 1 plus 1 plus 1 mod 2. 1 plus 1 plus 1 mod 3 gives you 1, 0. The element of order 2. Yeah, this is going to have order 6. The smallest positive integer n such that n 1, 1, which is analogous in multiplicative notation to raising to the nth power, equals 0, 0 is n equals 6. The order of 1, 1 is 6. Likewise, the order of 1, 2 is also 6. Those are generators of this group. This group is cyclic. So while Z2 external direct product with itself is not cyclic, it's not isomorphic to Z4, the external direct product of Z2 and Z3 is cyclic. Interesting. Do we have a conjecture about what might happen in general here? One conjecture you might make is if these are the same, maybe you get a cyclic group. And if they're different, maybe you get a, or maybe you don't get a cyclic group, but if they're different, maybe you do. That might be one conjecture. It's actually not quite right. It's related to whether the subscripts are relatively prime or not. Is ultimately what you're going to see as you go through the reading, chapter 8. If the subscripts are not relatively prime, it won't be cyclic. I guess I'm telling you the answer. If they are relatively prime, it will be cyclic. Which should make some basic intuitive sense based on past experience, perhaps, to expect such a thing. And yes, you can form the external direct product of more than two groups. You can do a G1 external direct product with G2 external direct product with G3, etc. And now you're talking about a set of ordered n tuples, G1, G2, etc., up to Gn, where each G sub I is from capital G sub I for I equals 1 through n. You might even wonder if do you need to restrict it to a finite number of groups? Could you do the external direct product of an infinite number of groups? Is that possible? Well, yeah, possibly. But I think finite will be good enough for us. And this will be a group under component-wise multiplication as well. Would you ever want to multiply elements here instead of adding them to get a group? Well, only if you're dealing with non-zero real numbers as the components, right? R is not a group under multiplication. The number zero kind of messes things up because it doesn't have a multiplicative inverse. R star is a group under multiplication where that means take away that problematic zero. That's a group under multiplication. So you could consider R star cross with itself, or in our book's notation, external direct product with itself. And that would be a group. It would not be isomorphic to this additive group, though. Would it be isomorphic to maybe the non-zero complex numbers under multiplication? You might wonder. Well, complex multiplication is not really done component-wise. Complex number multiplication, A plus BI times C plus DI, is done using FOIL, first times first, outside times outside, inside times inside, and last times last. And then replace I squared with -1 and rearrange. This becomes AC minus BD plus AD plus BCI. And if you thought of complex numbers as being ordered pairs instead of sums like this, which you can do, you can think of complex numbers as ordered pairs if you want. Geometrically, we visualize complex numbers as a plane, with the horizontal axis being labeled with the word real and the vertical axis with the word imaginary. You could define component-wise multiplication. Well, I shouldn't call it component-wise. You can define a multiplication in this way. That's not component-wise multiplication. That's not AC there and BD there. It's a more complicated kind of multiplication. But it is a multiplication. That is the true multiplication that is done in C star. So you'd probably suspect because of that, this might not be isomorphic to C star across the external. No, this is not necessarily isomorphic to C star as a group. As sets, you could say they're, well, they're still not, let's see, they're still not even the same as sets, really. Because when you cross this with itself through the Cartesian product, you're not just getting rid of the origin in the plane, you're getting rid of the entire X and Y axes. Because neither component can be zero. So it's not even quite the same as sets. All right, in our last 15 minutes here, again, let's look at the textbook, chapter 7. And I just want to highlight some things to just pay attention to and try to, and even try to enjoy, you might say, and some things that are important for later. Starting with the properties of cosets here, this is page 139 if you want to follow along with me. One property that I did not really focus on the other day, Monday or last Friday, did not really focus on property 6. But property 6 is actually pretty important. I equals ha, in other words, the left coset of H and G containing A and the right coset of H and G containing A are the same, they're equal as sets, if and only if H is the same as this set. Where this set, A inverse, not quite aha, but sort of aha, is defined to be as a set, the set of all elements of the form A times A times A inverse, where little h varies over capital H. This is sometimes called, in general, a subgroup conjugate to H. You can prove it's a subgroup actually, no matter what A is, as long as H is a subgroup. H is a subgroup of G implies this set is a subgroup of G. You could use one of the subgroup tests to verify that, and I would encourage you to do so. It's not necessarily equal to H in general. In general, A inverse, this subgroup conjugate to H, is not equal to H. It will be a subgroup of G, but not necessarily H. Though its order will be the same as the order of H, which should make intuitive sense. I mean, you're letting a little h vary over capital H. Yeah, that's got to be true. When it does equal H, the case where capital H, A inverse does equal H is very special. And important. In this case, we say capital H is a normal subgroup of G. And normal subgroups are super important and are the main topic of chapter 9, which we'll get to shortly after spring break. Chapter 9, title is Normal Subgroups and the Factor Groups. Very important topic. Okay, that's just some background, but I would encourage you as one thing you do in your reading time before Friday or maybe before Monday after spring break is trying to verify that this is a subgroup when H is. And so property 6 are two equivalent conditions for when H is normal. When H equals A inverse, that's equivalent to AH being HA, the left coset being equal to the corresponding right coset. Whether H is normal or not, certainly both of these sets contain A itself. Question is whether the other elements are the same. I'm going to move ahead to, well, I'm not going to talk much about Fermat's little theorem other than just to highlight that the fact that it's got a name is important. This is a pretty important theorem. And if you're encouraged to explore, if you have a desire to explore, I would encourage you to see if you can search out some information on what are called Rsa codes. RSA are in the initials of 3 people who did work back in the 1970s to create modern day cryptography, modern day cryptography method that is very much used today still to keep transactions on the internet secure, for example. And RSA codes and other coding schemes that they're trying to make new ones that are even better, especially with quantum computers coming along, is based on Fermat's little theorem. The truth of this fact is what makes RSA cryptography work. If that's something you'd like to explore. We did have somebody here during this January do that for their senior seminar project, right? about cryptography and art and Fermat's little theorem. It was Aaron Yant, if you know her. Next page. Example 5 is pretty important and is something I've emphasized in the lectures. Converse of Lagrange's theorem is false. I mentioned that already before. Just because a number divides the order of a group does not guarantee there's a subgroup of that order. And the simplest example is in A4, which has order 4 factorial divided by 2, 12. Alternating group on 4 objects. Those are the even permutations. It's got no subgroup of order 6, even though 6 divides 12. Very nice little argument for that. That, you know, when you read these things usually at first, you typically feel confused. And to be honest, I often feel confused. I hope that's actually encouraging, because what that means is you need to go back, including me, I need to go back and be more careful to try to understand this. And you can understand it if you take the time. But you got to have the time, which means you need to, of course, then be organized with your time. Some people are very organized, some people are not. To tell you the truth, I'm not super organized with my time. I try, but yeah, I'm not the most organized person, as you know, from my office not being super organized either, if you've been in there. It's related to, it's an argument by contradiction. It's related to the fact that Cosets partition, which reminds me, I meant to say, this is always a subgroup of G when H is, but the left and right cosets are not necessarily subgroups. Only when A itself is in H is a left coset AH or a right coset HA actually a subgroup. It equals H itself when A is in H. But in general, cosets are not subgroups. But this thing is, this conjugate thing. Okay, so it's an argument by contradiction, very nice little contradiction, and it's using the fact that the cosets partition. And if you assume H has order 6, that would mean there would be 2 of them that partition the group of order 12. These are non-overlapping, their intersection is empty, and their union is the entire group. And that leads to a contradiction. This theorem is pretty useful. It doesn't have a name, but if you work at it, you can pretty easily remember the formula. The order of HK, where HK is defined to be this set, and this is evidently not necessarily a group, perhaps. It can be it's not necessarily a subgroup. It can be a subgroup, but you need extra conditions on H and K for it to be a subgroup. But its order, its number of elements in the finite group case, when H and K themselves are finite, is the order of H times the order of K divided by the order of H intersect K. And again, H intersect K will be a subgroup of G when H and K are. This argument is not too bad at first, but once you get down here, then it gets a bit tricky. But yes, once again, you can understand this if you put the time into it. It's got some pretty nice applications. And again, this is what group theorists love, especially those who specialize in finite group theory. These kind of arguments, these kind of counting arguments based on prime factorizations and divisors allow you to conclude many things that would be completely surprising based on just the initial definition of a group, that you get these kinds of things. So this example here is pretty nice. A group of order 75 can have at most one subgroup of order 25. Again, so that's just a fact that as it stands by itself is maybe not necessarily super important, but it should just be astonishing. You should be in awe and worship God because of the nature of reality in group theory, and that's God's creation, that, yeah, based on just the definition of a group, and the order of an element and the order of a group, that any group of order 75 can have at most one subgroup of order 25, whether the group of order 75 is cyclic or not, evidently. Certainly cyclic group of order 75 would have a unique subgroup of order 25 by the fundamental theorem of cyclic groups, but no assumption that G is cyclic. You might also wonder whether G would have to be cyclic if it has order 75, but that's another issue. And it's using this theorem here. Suppose you've got two subgroups of order 25. What would this theorem imply? Well, their intersection, again, is a subgroup of G. Therefore, its order has to divide the order of things it's a subgroup of. I guess G itself is not necessary to focus on here. H intersect K is a subgroup of G, but it's also a subgroup of H because it's a subset of H and it is a group. It's also a subgroup of K. The order of H and the order of K is both 25, so this has to divide 25. So it's 1, 5, or 25. Ultimately, we're going to conclude that it's 25. We're going to show that the assumption that it's 1 or 5 leads to a contradiction. If it's 1, then this theorem implies that the order of this set HK is 25 times 25 divided by 1, which is 625, which is impossible because G only has 75 elements. If it's order 5, divide by 5 instead, you get 125 elements, which is still impossible because G has only 75 elements. Can't have more elements in the set HK than there are elements in the entire group. Those both lead to contradictions. Therefore, we are stuck. We are forced to conclude that this has order 25, which is the same as the order of H and K themselves. Therefore, they must be the same subgroup. Because we're assuming there's only one, or well, yeah. Because, okay, needs a little bit more there. H intersect K is a subgroup of H and a subgroup of K. If it's got order 25, the same order of both H and K, then they have to be the same. H and K are the same. H intersect K is also the same. They're the same set. This one's a pretty long proof, but it is understandable if you put it in the effort. And it's a classification fact. Any group of order 2 times a prime not equal to 2, P is a prime greater than 2, there's only 2 possibilities of what it's isomorphic to. It's either cyclic or it's a dihedral group up to isomorphism. So any group of order 6 is either isomorphic to Z6 or D3. P would be 3 in that case. Symmetries of a hexagon. Would be D3. Wait, did I say that right? Oh, D6, yeah. If P, I meant to, okay. If P is 3, then it's either isomorphic to Z6 or D3, symmetries of an equilateral triangle. If P is 5, it's isomorphic to Z10 or D5, symmetries of a regular pentagon. If P is 6, it does not. This does not apply to the case where P is 6 because 6 is not prime. If P is 7, it's either isomorphic to Z14 or D7. Only 2 groups of order 14. D7. What's a regular n-gon of 7 sides? I don't know what it's called. Etc. I would also, just in 5 seconds here, very strongly to encourage you to really make an effort to understand the Orbit-Stabilizer Theorem and its proof. I have given at least parts of the proof of the Orbit-Stabilizer Theorem on past exams. It's not an easy proof, but it is something you can, again, understand if you put the effort in. And it's worth putting that effort in. All right. So I won't see you until after spring break. So unless you want to stop by my office through tomorrow. So have a great spring break.